Hello, this is Prof. Nanius, and this is part of our prerequisite series for differential equations. And today we're going to talk a little bit about gradients. And let's see. So here we go. So this is the idea behind a gradient, and I have a little example written in my paper here. So let's say we have a simple example. Let's say f of xy, a two-variable function, like we learned in Calc 3. Let's say it's x squared y plus y e to the x. Nice and simple. Now the gradient of f, as you learned in Calc 3, is going to be the partial derivative of f with respect to x times the vector I plus partial derivative of f with respect to y, j, where you remember that in two variables, I will be the vector 1, 0, and j will be the vector 0, 1. Okay, so in this case, the gradient here can be computed simply. Partial with respect to x, it's 2xy plus y e to the x, I, plus the partial with respect to y, well, that's going to be an x squared plus partial with respect to y e to the x, j. And that's kind of how, I mean, I know this is a relatively simple function, but keep in mind that this is in fact a vector. You know from Calc 3, if you have a specific value of x and y, at that point in the plane, this gives you the direction of the greatest rate of change. Um, but that's maximizes the directional derivative, but that's, aside, that's a sort of aside from what we want right here. But that's a gradient. Now, what we're going to be given is the following question. And keep in mind, such a thing here is called a vector field. So suppose, for example, if you have a vector field now, where you have p of x, y, I, plus q of x, y, j, you want to know, is there some f where the gradient of f is equal to this particular vector field? Now that's going to be a question that's important to us. Now here's the thing. Suppose this given vector field here was a gradient. This means that this thing right here, if so, this p of xy is going to be the partial derivative of some two-variable function f with respect to x, and q of xy would have to be the partial derivative of f with respect to y for some f, if that were true. So if that were true, this must be true. Then you learn from Calc 3 if some reasonable conditions about the partial derivatives being continuous. If I partially differentiated this now with respect to y, that's f of xy. And if I partially differentiated this with respect to x, that would be f of y, sub yx. And you know that if at a point where there's an open set and these two things are continuous, then these are in fact equal. So our condition is that, and it turns out that's an if and only if. I'm not going to get into the reasons why, but this is true if the partial of p with respect to y is equal to the partial of q with respect to x. This is sometimes called exactness. And we'll be using that later in our particular course. Now, of course, the question attains here, and I do have an example written down that I want to do. At least thought I did. The question is like, well, suppose we say, let's say we're given an example f, and let's say it's going to be, let's say e to the x plus y I plus, let's say, sine of y plus x j. And so you want to know, find f where the gradient of f is big F. And that is sometimes called solving a differential equation. Now, one of the things you note if you take this with respect to y, that's 1. And if you take this with respect to x, that's also 1. So this is exact. So how do we actually find this little f? Well, remember, this thing here is partial of f with respect to x. So if you take the partial of f with respect to x and integrate it with respect to x, you'll get something. Same thing if you take this and integrate it with respect to y. And up to a constant of sorts, these two ought to be equal. Now, the verbiage might be a little confusing, but the actual practice isn't. So let's just try to integrate this thing here with respect to x. Well, the integral of e to the x is e to the x. The integral of this with respect to x is yx. And then the constant here is going to be some arbitrary function of y. So this is a plus c that you learned in Calc 1. Because remember, if you partially differentiate something that's purely a function of y with respect to x, you get 0. Similarly, if I integrate this with respect to y, the antiderivative is going to be minus cosine y plus xy plus some function which is exclusively of x. Now, our goal is to match these two. Match this one with this one. And it turns out you can. One such f will be e to the x, that's this, plus xy, that's this one and this one, minus cosine of y, and then you can just add a constant at will. A pure honest-to-goodness constant, not a function of xy. But this works. This works for all k. And you can use k equals 0, k equals 1, k equals square root of 2 divided by 10 to the third, whatever you want. So that's how you do that. So thanks for watching.